Now in this video we're going to look at a number of experiments which are going to require an explanation using Faraday and Lenz's law of electromagnetic induction. You should have a worksheet that details the basic experiments, and what we're going to do is we'll have a look at those experiments and you can try and fill in your explanation for each one. So if we look at the first experiment, what we have here is an aluminium ring suspended from a string, and we're going to place some magnets in the ring. We're going to pull them away from the ring. Now aluminium is not a magnetic material, unlike steel. A magnet won't be attracted to a magnet, but here when we pull the magnet away, you can see there that the aluminium ring follows it, and we start the aluminium ring swinging from side to side. Can we explain why that is occurring using Faraday and Lenz's law of electromagnetic induction? There we go, we see it again. So we move the magnet either into or out of the aluminium ring. That will start the aluminium ring swinging. And there we see the effect once again. Now if I try the same effect, instead of using magnets, just use a little iron rod here, you can see basically that there's very little effect on the aluminium ring at all. So it only works when we're using actual magnets. And here we've got an aluminium ring again, moving the magnets, but this time we've got an aluminium ring with a slit in. So unlike before where we had a complete aluminium ring, this time there's a slit in the aluminium ring. When we pull the magnets away, you can see it has very little effect on the ring. Now in experiment 2, we've got a simple electrical circuit here, and basically we're using the blue wires here to connect an iron cord coil to a 1.5 volt cell, and then we've got a neon lamp in parallel with that coil. Now it is important to realize here that the neon lamp needs about 70 volts in order to light. So if we turn the switch on, connect the circuit by flicking the switch here to the upwards position as you look at it. As we do that, nothing happens. Okay, we've only got 1.5 volts. But when we open the switch again, you'll see the neon lamp lights briefly. So there we've turned the circuit on, now off, and you'll see as we turn off, the neon lamp lights. Can we explain that using Faraday and Lenz's law of electromagnetic induction? Why is it here that when we close the switch so that a current flows in our circuit, we have the neon lamp doesn't light at all, but then when we disconnect the circuit by opening the switch, we see that the neon lamp lights briefly. Bear in mind the neon lamp needs 70 volts across it, around about 70 volts across it, in order to light. Experiment 3, what we have here is a aluminium plate, and on the left we see basically we've got a powerful electromagnet. Okay, so the coil there, we've got a coil on an iron core, and we've got 2 pole pieces on top of the U-shaped iron core. There are 2 pole pieces, and between those there will be a powerful magnetic field. What we're going to do is we'll pull that aluminium plate backwards, and we will start it swinging between the pole pieces. Now to begin with, we haven't turned on the power supply yet, so the magnetic field isn't up yet. What we're going to do is just allow that aluminium plate to swing, and then we're going to turn on the power supply to power our electromagnet. Let's see what happens, and you can see the aluminium plate is rapidly brought to rest. Why is it then? Why is applying that magnetic field rapidly bring that swinging plate to rest? Can we explain that using Faraday and Lenz's law of electromagnetic induction? That is experiment 3 on that worksheet. Try and do the explanation. Now we're going to turn the plate around the other way. So this time we've got little slits in the bottom of the plate. We're going to swing it again. We're going to turn on the electromagnet again. And the magnetic field will gradually bring the plate to rest, but it will bring it to rest much more slowly than it did before. Why is that? How is putting the slits in the end of the plate affecting it? What electrical property is being affected here for the plate? Why does that mean it takes longer for the magnetic field to bring it to rest? Now in experiment 4 we have another electrical circuit. Again, the circuit diagram here is shown at the bottom. So we've got two branches to this circuit. The first, on both branches, we've got a filament lamp. Okay, they're identical filament lamps. But in one branch, the one that's connected in with the blue wires, the filament lamp is in series with a variable resistor. And in the other branch, the one connected with the red wires, it's in series with an iron cord coil. Now it's important to realize here that the variable resistance has been adjusted so that its resistance matches the resistance of the iron cord coil. So that being the case, because they're in parallel, the power supply will put the same voltage across each branch of that circuit. Both filament lamps should light to the same brightness. They're identical filament lamps. The resistance of each branch of the circuit is identical. We're putting the same voltage across each branch. Both lamps should light to the same brightness. So we'll turn on the power supply and we'll see that. So we'll just basically close the switch and you'll see the lamps light. What's interesting though, if you look, one takes slightly longer to light than the other. As we turn that on, can you see that the switch, that the filament lamp on the right there, that's the blue circuit, that's the one just with the variable, the resistance in, lights immediately, but the filament lamp in the branch of the circuit with the iron cord coil in comes on slightly after it. It's a slight effect, but it's nevertheless visible if you look closely. Can we explain, using Faraday and Lenz's law of electromagnetic induction, why it takes slightly longer for the filament lamp in the branch of the circuit with the iron cord coil? Why does it take slightly longer for that lamp to attain its full brightness? So here we have experiment 5. Now what we've got is a copper tube, and I'm just dropping an unmagnetized steel cylinder through that tube. Okay, you can see there it's not magnetized, it's not attracting the ball bearing, and it drops quickly through the copper tube. Now what we've got now is a magnet. You can see it's sticking to the stand, it's magnetized, it'll attract the ball bearing. We're going to take the magnetized cylinder, we'll drop that through the copper tube, and look how much longer it takes to actually travel through the copper tube. We drop that magnetized cylinder, okay, it's a magnet, we drop it through the copper tube. It takes much longer than you would expect to travel through the copper tube. Okay, and then again we can see it's magnetized, it's attracting the ball bearing. If I take the unmagnetized cylinder, it doesn't attract the ball bearing, and drop that through, you can see it drops through there in a fraction of a second. So why is it then that it's taking much longer for the magnet to drop through the copper tube? Can we explain that using Faraday and Lenz's law of electromagnetic induction? Remember, copper is not a magnetic material like iron, so the reason that the magnet is attracting the ball bearing is that the steel that the ball bearing is made of will be attracted to the magnet. Okay, the magnet won't stick to the copper tube, it won't attract it. So we've got to explain using Faraday and Lenz's law why it is it's taking the magnet to travel longer through that tube. Okay, experiment 6 then. What we've got here is a power supply. We've got a coil of wire that we've put here on the retort stand. And we've got an aluminium ring that we've put on top of the coil. And to begin with, we've connected the coil to a DC power supply. So we turn on the power supply, and when we turn on the power supply, very little happens. There's an initial shaking of the ring, but then it just sits there on top of the coil. I change it across to AC, however. What do we see? The aluminium ring levitates on top of the coil. And you can see there, it's standing up way above the coil. If I take the aluminium ring off and put another aluminium ring on, which has got a slit in it though, that just rests on the coil. It doesn't do anything at all. It doesn't levitate whatsoever. Take that off, put the complete ring on, and there you go. Now what's interesting as well, if I touch this ring as well, it'll be starting to get warm. That gives you a clue as to what is happening. The aluminium is really beginning to get quite warm. The ring with the slit in stays cool, doesn't get warm at all, and it just sits on top of the coil. Oops. And then we put the complete ring on again. You can see the difference. The complete ring is levitating, provided we've got an alternating current in that coil of wire, but the ring with the slit in does nothing. And there we are, levitating aluminium ring. Can we explain that effect using Faraday and Lenz's law of electromagnetic induction? Why does it need a complete ring, not a ring with a slit in? Why does it need AC and not DC to exhibit this effect? Finally, experiment 7. What we have here is a tube passing through a coil of wire. The coil is just connected to a digital oscilloscope. Okay, now the oscilloscope will measure any voltage that is across the coil. So what we're going to do is we're going to drop a magnet which is going to pass through, it's going to fall through the coil of wire, and we're going to record any voltage here on the computer screen. So the oscilloscope, digital oscilloscope that's connected to that coil, will measure any voltage output from the coil. Here we go then, drop the magnet through, and hopefully on the screen there you can see the trace that's been produced. So what we've got there initially is a positive voltage produced, okay, and then that changes to a negative voltage. The magnitude of the negative voltage is actually, if we look closely at that screen, slightly larger than the positive voltage. Okay, so as the magnet falls into and out of the coil, we've got a positive voltage, and then a slightly larger negative voltage gets produced, but the negative voltage doesn't last quite as long as the positive voltage did. Okay, so there's a couple of things there to try and explain. Why do we get first a positive voltage and then a negative voltage? Why is that being produced? Why is the negative voltage that's produced secondly, why is that larger? Why does it not last for quite as long? Can we explain those things using Faraday and Lenz's law of electromagnetic induction?